So almost all of you saw the sun. Some of you didn't see the sun. And what did for those who missed out, what did you see? Somebody, maybe all together. What did you see? Not much. You saw the sun. This is the middle of January in Vancouver. That was a miracle. A miracle. You saw the sun. You might be complaining, but I learned recently in Moscow during the month of December, I don't know if it's gotten better. Do you know how much sunlight they got in December? Like how long it was sunny in December in Moscow? We think we have it bad. You heard 6 minutes, which is better than none. But 6 minutes. Oh my goodness. So you guys just now experienced more sun than the Muscovites did in the entire month of December. Courtesy of me schlepping you out there. Like 3 times more, in fact. You were out there for 20 minutes. So what did we see of the sun? So the things that were important maybe were, first of all, the size of the sun. When you did this, if you held up your pinky, you could easily cover the sun. So the sun is about half a degree across, which means we can estimate how big it is physically, right? Just like you measured the height of the clock tower, right? Did anyone climb it? You did? You have a helmet. You might have climbed. That's your helmet. So you did climb it. Okay, well that's cool. So the sun subtends half a degree, and it's 150 million kilometers away. So if we do the math, right, a half a degree is, remember that formula? It's like angle in degrees divided by 57. Gives us an idea times the distance is the size. So my angle in degrees, it's half a degree divided by 60 because I'm not that good at math. So that's 150 divided by 120 million kilometers. So 150 divided by, 150 divided by 120 million kilometers is maybe 1.2, 1.3 million kilometers in diameter, right? So that gives us an idea of the size, right? It's about 1 million kilometers in diameter, the sun, and that would be one thing we could have measured today by covering it with our pinky. The other thing that you noticed was, which I told you to notice, was that it's darker near the side. Now imagine if the sun were a ball, whatever. Just imagine it's a yellow ball like you drew in school, right? It's a yellow ball and you draw the sort of things flying out, but you don't have to do that. Yellow ball. If you wanted to be darker at the edge, right, you would just color it darker at the edge. But then when the sun rotates, what you would see is a big stripe along the middle, right? If it's a solid object. Do people understand that? If the sun were a solid object and it were darker at the edge today, in a few days, that stripe would have rotated and you would see a stripe not at the edge, but sort of a quarter way across. So the fact that so what people realized as soon as they made the telescope, Galileo would look at the sun, but he would project it onto stuff, but he also looked at it to aim it. So he damaged his eyes. But generally, you project on it, and he saw sunspots, and you could see that the spots moved over the course of a week. Today, we saw no sunspots. So they realized almost immediately the sun is rotating about once a month. So there in 310, who took 310? Anybody? Did you measure the rotation rate of the sun? Maybe it was maybe not this time, but yeah. So you look at the sunspots when the sun's cooperative. Was the sun cooperative for you guys? Can't remember. I know sometimes there are no spots like today, and then they use some, website, but it's more fun to to actually see the spots. So they realized the sun rotates about every 30 days, and then you could go, well, if it were solid and it's darker at the edge, then that stripe would move along with it. So you could realize almost immediately that it's gaseous, right? It's not a solid ball. And then third thing that you may not have noticed is it's a circle. It's like the most round circle that you've probably ever seen. It's so close to a circle, we really can't measure its deviation from its circularness. That's pretty cool. So it's almost a perfect circle. I can't say it's precisely a perfect circle because that would be perfect, but it's very close to a circle. And that's kind of cool. Why is it important that it's almost a perfect circle? Has to do with what its gravity looks like for the planets, for example. But it's also just cool to think of it as the most perfect circle you've ever seen. There are objects in space that are even closer to a circle. But the reason why it's so circular has to do with that gravity is what's holding it together, and it's a gas. So it's a fluid, so it can't really resist, like make a big lump over here if the gravity will just pull that flat. On Earth, we have mountains, and so the mountains can hold up under their own weight because they're solid. On the Earth, it's rotating a lot faster than the sun. It rotates once a day. So the Earth actually isn't a circle. It's more ellipsoidal. And if you look at a planet like Saturn, which rotates, I think every 9 hours. If you look at it through the telescope, you go, that ain't a circle. It really is noticeably squished. But the sun rotates every 30 days, which doesn't really change its circularity very much. So our sun is our own star, so that makes it quite special. It's 300,000 times closer than the next nearest star, which is a red dwarf called Proxima Centauri. And believe it or not, the nearest star, and even the nearest star is in a triple system, and we think that those stars have planets too. So planets are really ubiquitous in the solar system. I mean, in the galaxy. Of course they're ubiquitous in the solar system. There are a bunch of planets here. But the key is we know lots about the sun, meaning we have lots of data about the sun. It doesn't mean we understand everything that's going on about the sun. There's still puzzles, and we still are changing our ideas. And in a certain sense, we probably know more about it than, well, obviously than any other star, but possibly more than all the other stars combined. So we often use the sun as a prototype to understand all sorts of phenomena in the universe, right? So of course the sun is a star, so we can use it to understand other stars. But the sun is also a big ball of hot gas. We can use it to understand how big balls of hot gas operate. Or specifically, the sun is charged. The electrons have left the nuclei for lots of the nuclei, even at the surface of the sun. So it's a plasma, and it's a diffuse plasma. What that means is that particles don't really run into each other that much, and most of the universe is in that same state of this diffuse plasma. And we can look at processes on the sun like the sunspots and solar flares and use them as analogies to understand completely different phenomenon in other parts of the universe. So it's really it's good for us to be near a star, because otherwise we wouldn't be able to live, but scientifically it's also good too. So just the things about the sun, and we've actually figured a bunch of these out, right? So the mass of the sun we figured out, right, in class. So it's 2 times 10 to the 30, a really big number, 2 times 10 to the 30 kilograms. Its radius, like we talked about, its diameter figured out in my head, a little bit over 1 million kilometers. Its radius, of course, is half of that, 700,000 kilometers. Okay? Now, it rotates once a month, precisely 27 days. So let's look at the other things about the sun that might be curious. As we talked earlier, it's about 6,000 degrees Kelvin. Right? We talked a bit about that earlier. We could guesstimate that here on Earth by just trying to make heat a piece of metal up to be the same color as the sun, right? And another way of looking at it, like if you ever look at when you're buying these new light bulbs, these LED light bulbs, or if you're into, if anyone's into like film or anything, like not watching film but making films, they'll talk about something called like the temperature of the color. So if you even look on an LED light bulb, it'll quote a number like 2,000 or 3,000 Kelvin. And that's meant to simulate a black body of that temperature. So if you wanted light, like the light like in the winter when we don't get the sun, you want something like a 6,000 Kelvin, which appears like, compared to the light in the house, quite blue, right? But that's the natural light. Okay? So that temperature is something we can measure here on Earth, as I described. So it's pretty high. Maybe next time I'll do an experiment where we'll create something here in the room that's about twice that temperature. That's okay. And it'll make like a loud noise too, so it's pretty cool. And it won't do you any harm, and you can do it at home. So that's all good, and freak people out at home if you want. Okay, but let's look at those numbers. The mass is huge. The radius is huge. Let's go to the temperature is pretty big, but I can do it here on this table if I want to make something that hot, and we will do that. There's nothing around that, the highest, melting point of anything is less than that number. So there's no material that it could be that's solid, at least no material that we have on Earth. So let's look at the density. Is the density huge? What do you think? Is that a big number or a small number for density? Does anyone have a sense of something about that density? Is it like the density of, like the most common thing that you can think of that's high density? Do you know what it is? Semi-common. Everyone thinks it's lead. Oh, it's lead. That's density of lead. That's heavy. You think of lead. Lead is dense and cheap. So that's why you think of it. Gold is really dense. It's almost twice as dense as lead. So gold, like if you had a ring that was gold-plated lead versus a gold ring, you would feel the difference in the weight quite easily. So gold, very dense thing. Do you think the sun is denser than gold? That number, 1,400 kilograms per cubic meter. You think it's denser than gold? Nobody thinks that. Okay, let's think of something that's not very dense, like the air in the room. Air in the room is not very dense. So is the sun denser than the air in the room? What do you think? Come on. You go, yes. So what is about that density then? It's somewhere between air and gold, you guys have concluded, right? What is the density of this thing? What is it, right? Okay. So does anyone remember like densities of anything? Water. So what's the density of water? 1 in what units though? That's 1,400. So that seems to be much bigger than water. No, but you're right. right? The density of water is 1,000 kilograms, or a ton, per cubic meter. So the sun is, on average, 40% more dense than water, on average. Now, in the middle of the sun, it's much denser than on the outside, and we'll see that. And furthermore, it's also much hotter in the middle than on the outside, right? Because what's holding the sun up against gravity, so we have surface gravity, is 28 times the surface gravity on Earth, right? So if you were standing on the sun, first of all, you can't stand on the sun because it's gas and because it's hot. You would weigh 28 times more. So the whole sun is being held up against its own gravity. And it can't be held up like the Earth is held up. The Earth is held up because it's sort of solid, right? You could imagine it's solid and hold up. It's not really what holds up the Earth, but you could imagine it that way. The sun is a gas, so what's keeping it from collapsing in on itself is the fact that if we take density times temperature, that creates pressure. Density times temperature is pressure, and if the pressure is higher as you go down into the sun, that increase in pressure will resist the force of gravity. So if we take the average density and the average temperature, that's not enough to hold up the sun. So if you think about it, you can figure out, well, what's the temperature or density in the middle of the sun, and it's going to be 1,000 times higher temperature, a little bit more than 1,000 times. The density is maybe 10 times higher, but we'll see that. So the pressure in the middle is much higher than at the surface. So, but that's how we can get some extreme things going on. The density isn't extreme, but we'll find that the temperature, as we go towards the middle of the sun, goes from something that I can produce here to something really large. So if we had a spectrograph, and maybe we should do this, that would be cool. So if I got a spectrograph, I could even we wouldn't use this thing. We could spread out the light of the sun on a board, and we would see something like this. So this isn't artificial. This is a real spectra. So the first thing you'll notice is the sun, it looks like a rainbow. Of course it does, because rainbows are sunlight spread into a spectrum. But if you looked at a rainbow really, really closely, you would notice that there are colors missing from the rainbow, right? It's hard to do with a rainbow on Earth, because when you go up to the rainbow, it always goes away, right? But here we can make the rainbow with a spectrograph, and you'll see that there's missing spaces in the spectrum. Let's see if we can see if there's anyone that is familiar to us, right? So we talked a little bit about some lines of sodium, which would be in this yellow region in here, and they come in a pair. So like one of these pairs in here would represent sodium, somewhere in this orange and yellow region of the spectrum. And here's the region where the sun is actually the brightest, where it peaks in the yellow. Okay, but we can see there's lots of these lines. Now the lines contain many elements that are familiar, and as I told you earlier, there are lines in there of elements that wasn't discovered yet, and they called that helium. So the funny thing about the sun is then you can go back and go, what is the sun made out of? What are the elements that comprise the sun? And well, we have helium there, which was a surprise, because we don't see much helium on Earth. And in fact, the helium on Earth comes exclusively or almost exclusively from radioactive decays in the Earth, right? So it comes in a different way than in the sun. So those heliums that we see on Earth are the very same thing that Rutherford used to shoot at the foil. It came from a radioactive decay. The helium in the sun was made, for the most part, at the beginning of the universe in a different way. Okay? Then there's oxygen, carbon, iron, silicon, nitrogen, magnesium, neon, sulfur, and all of those things are relatively common on Earth. The helium isn't. And what was somewhat surprising is, what was the number one element in the sun? I left it blank. Does anyone know what it is? It's hydrogen, right? So hydrogen, of course it's on Earth, but it's never by itself, because if I get hydrogen by itself, guess what it does? It just floats up. The same with helium. It'll just float up through the atmosphere and go away. So the hydrogen's always bound up in compounds, and it's not like the number one element on Earth. The number one element that we'll find, like if I get a bunch of rock from the surface of the Earth, does anyone have an idea what the number one elements, if I pick up some rocks, are? No, not carbon. Oxygen is in there. Silicon is in there. Aluminium, right? That's not, I mean, oxygen sure is interesting for us, but it's not, the other two don't play an important role in humans, right? The sun is actually made of what the universe is made up on average. I mean, there's slight differences, but that's what the universe is made up on average. The universe is of the stuff we know about. The dark matter, we don't know what it is, but of the normal stuff, the universe is mostly hydrogen, then helium, oxygen, carbon, nitrogen. The most common elements in you are hydrogen and oxygen and carbon. And the most common elements in the sun are hydrogen, not helium, carbon, and oxygen, just like you. If we go down the list, iron is important in you. You know that. Silicon, not so much, although we pretend that we rely on silicon a lot, but we don't really need it. But nitrogen, magnesium are also important for you, and sulfur is important for you. So the things that are in the sun that are common are actually the things that are important for life, amazingly enough, and that's no coincidence, right? But we are made out of the most common elements in the universe, more so even than rocks. That's kind of cool. Now, the other ones that are common in the sun that aren't common in you are helium and neon, right? And those aren't common in you because they don't make chemical elements, right? They don't make chemical compounds. So they're gas, and they would just get lost from your body, right? So helium, you know, like anyone do the helium and make their voice funny? You've not done that? Then like I'm always picking on her. She'll be sitting back behind a pillar next time. But the point is helium doesn't really react with your body. You can easily suffocate, but helium doesn't do anything for you, and neither does neon, because it's in that rightmost column where they aren't reactive. Okay, so a few weeks ago, we measured what we call the solar constant. You might not know that we measured the solar constant, but that's what we did. And that was the experiment with the light bulb, right? What we did is we saw how much energy the light bulb was putting out, and then we moved our hand to a given distance from the light bulb where it felt like the sun. And what that told us was the amount of energy per square meter that comes from the sun. So this number is a little bit over a kilowatt per square meter. So that could give you an idea, like if you wanted to get all the power of all of our needs on Earth, if you think about a big power station that makes a lot of power, it is about a gigawatt, a billion watts, right? So if you wanted to replace a big power station, right, you would need an area not 1 meter squared, but you would need something 1 million times larger because 1,000,000 times 1,000 is 1,000,000,000. So you would need an area of solar panels 1 kilometer on a side. So if you think about adding everything up in the whole world, you would have to need solar panels about 100 kilometers or so on a side for all the energy needs of the world. So the sun is giving the Earth much more energy than we need as humans, of course. But then we burn crap, so we screw everything up. But if we could use the sun, basically you'd have to put solar panels over some small fraction of Arizona, and no one would miss it. No one would miss that part of Arizona. So this number includes all of the radiation that we get from Earth, not just the heat, which is what we were sensing with our hand. And it measures the amount of radiation that hits the top of the atmosphere, not what's reaching the surface. So we can use that to estimate what is the the total energy output of the sun, which is what we did. And our estimates were close, mainly because the light bulb that we used, we didn't use a 100-watt light bulb, we used a 60-watt light bulb, but it's designed to mimic the spectrum of the sun. So we're going to compare this with what we do on Earth. So the people of the world consume 1.5, about 10 to the 13 joules of energy each second. So that would be 1.15 terawatts, 15 trillion watts. So like I said, it wouldn't actually, that 100 by 100 kilometer thing in Arizona nominally would produce, well, I said 10 kilometers. That would produce 10, we said 1 gigawatt per square kilometer. So that would produce about 14 terawatts, that 100 kilometer area that I talked about in Arizona, 100 kilometers on a side. So you can see that's where that number is the same, right? So it's not a large amount compared to the how much the sun delivers. So if we think about it, if we wanted to blow things up, we always like blowing things up, that would be 14 kilotons of TNT every second. So what does that mean? So a ton of TNT would be about 1 meter on a side. 1 meter on a side, right? It's about a ton of TNT. So if we wanted a kiloton of TNT, that's 10 meters on a side. It ain't that big, and 4 kilotons would be a little bit more than 10 meters on a side, or about that. So like boom, boom, boom. It's a big explosion, but imagine it's that chemical energy we could put in something a little bit bigger than this room. Just releasing it very quickly would be kind of scary. Now, on the other hand, what the sun does in a second is deliver about 43 megatons of TNT every second, which is about the largest nuclear device ever exploded. And I'm using these nuclear devices because, of course, the sun does it in the same way as these nuclear devices. So it's a huge amount of energy that's spread out over the entire Earth. And essentially, even if we couldn't make very efficient solar panels, you have to think about, well, how could we make them? If you just put them in Arizona, of course, they'd only be in the sunlight half of the time, and the sun wouldn't be overhead all of the time. So we put in 25% efficiency, but in reality, it would be a little bit lower than that when you think of weather and stuff. But you can see it's not a huge area, would meet all of our energy needs. Not just generating electricity, but the airplanes flying and the trucks driving and everything else that we do. So what powers the sun? So basically, you know, the idea of actually what powered the sun wasn't solved until even less than 100 years ago. But people, of course, looked at the sun and wondered what was going on. And if you look a little bit more than 2,000, almost 3,000, that's 2,000 years ago. A Greek philosopher said, well, the sun is a burning hunk of metal. So some really hot metal that was glowing. And you can see with time, things didn't evolve very much. If you thought just at the end of the 19th century, so just a little bit more than 100 years ago, people were saying, well, the sun is a burning lump of coal. It really just reflected what people thought of as hot, glowing objects at the time. And we know both of these things, ideas, there the sun is solid and somehow glowing, and we know from our observation of the sun that neither of those would work, that in reality it has to be gaseous. It has to have an atmosphere. But we want to figure out, well, how is the sun making its energy? So one thing to think about is how much energy it emits for every gram. So is it emitting a lot of energy per its mass, right? We operate on chemical energy, and so you could imagine if this could be a really large number and very hard to explain how to get so much energy with so little mass, or it might not be. And we went through this exercise a while ago, and we have a very large amount of power coming out, but we also have a very large mass. So when we divide those out, we get about 2/100ths of a watt per kilogram. And when we compare that with things that use chemical energy, it seems to be a relatively small number. So if you imagine you have a candle, the power out of a candle might be 10 watts, but its mass is really small. And we did our example of ourselves, right? So for ourselves, we are about 1 watt per kilogram, and the sun is 1/100th of this. So chemical processes like burning stuff can produce that much power with the mass of the sun. But the question is given the amount of fuel, the mass of the sun would represent a certain amount of fuel. Let's imagine it was coal. How long would it take the sun to burn out, to burn through all of that big hunk of coal? How long would it take? And it would take about 20,000 years. So if you believe the sun is older than 20,000 years, well, it's not going to work because, and we have evidence that the Earth has been around for a lot longer than 20,000 years. So at that time, people thought the Earth was at least millions of years old. So you could come to the conclusion that the sun is not powered by chemical energy. It's not powered by chemical energy. So this idea of it being a burning hunk of coal or some metal that's kept hot by chemical energy just doesn't make sense. So Waterston made this calculation, and he proposed a different idea for what's heating up the sun. And what he felt is there are rocks. We have rocks hitting the Earth all the time, and when they hit the Earth, they streak through the sky and they make a lot of energy. So what's happening is, as something falls onto the sun, it gets going faster and faster and faster, and then it hits the sun, and all that energy in its motion would get converted to heat. So this is what he argued was going on. So you could ask yourself, how long will this work? So you could say, the sun is a given mass right now. How much energy could have been released by bringing material onto the sun, because when I bring a gram onto the sun, it'll release a given amount of energy, and the sun has a certain mass, so we can calculate how much energy could be released by forming an object like the sun. So this was a bit more sophisticated calculation than Waterston did, but it's to figure out whether that makes sense. So Lord Kelvin, who the temperature scale is named after, Kelvin wasn't the name he was born with. Kelvin is a river in Glasgow. So we can think about how long the sun will last. So we have an energy on one side, which we have to figure out what it is. The power, we know. We calculated it in class, right, with the light bulb. And we want to figure out the time, is the thing that is how long the sun can last with that energy supply. So to make this work, we already know the power, but we have to figure out what is the amount of energy with the idea that it's supplied by gravitational energy. So we know the power. What's the energy? So I'm just going to give you the formula, but we can think about where it comes from a little bit. So first of all, if I have two objects, there's a gravitational force between them. So the gravitational force is the mass of one object times the mass of the other object divided by the distance squared times the gravitational constant. So those ingredients, if you think about that, that would give you G and 2 powers of M and 2 powers of R down the bottom. You may or may not have remembered this from classes you've taken before or in high school, is that energy, or we call it work, is a force over times the distance is energy. So that, if you think about the energy to bring two objects that's released by bringing two objects together, that's big G times the mass of one object, the mass of the other object, divided by the distance between them, not the distance squared. So that's why this total energy that the sun, if we bring all the material of the sun together into a sphere, that's how much energy would be released, meaning negative of that would be the energy that's being released. So we know the big G, we know the mass of the sun, we know the radius of the sun, and we know the power. So we can calculate, first of all, what is the energy that would be released if we were to bring all this material that made up the sun by throwing comets down and meteors and building up a bigger and bigger ball until it's the mass and radius of the sun. And that amount of energy is 2 times 10 to the 41 joules. I could do the math on the board, but I think you guys are pretty familiar with how it works. But we have the mass squared would be some number like 10 to the 60, because the mass is 10 to the 30, and the radius, if we remember, was 10 to the 8 or so. Oh, and then we have to remember what G is. You could just trust me that that's the number, and that actually makes sense. Okay, so we have 10 to the 41 joules. Again, it's a really big number, but we also have a really big power. So what we have to do is we have to divide the energy by the power, and that tells us a time. Yes? Why is there a 3 over 5? So that has to do with the fact that if we think of the sun as being a ball, not every bit of the sun is one distance r away from every other bit. You get that number by summing up all the little bits of the sun and asking what's their energy relative to each other. Okay? So like I use this idea, like if I had two things the mass of the sun and I brought them one radius apart, it would be G m squared over r. But in reality, that's not how the sun is built, right? There's mass all the way through the sun. And that number is assuming it's just a ball that's equal density throughout. Okay? So it's just there. You could think of it as 1. In reality, it may be a little bit smaller than that. But as far as our argument, it doesn't matter whether it's 3/5 or even 10. You'll see in a second. That's how astronomy works, right? Usually things just don't work. When they don't work, they really don't work. They aren't even close. So we can take the energy and divide it by the power. And we'll get, so power is joules per second. So when I divide joules by power, I get 5 times 10 to the 14 seconds, which seems like a big number. It's a big number, but if you put that in years, that's 18 million years. So you go, okay, Waterston would have done this, and at the time Waterston made his initial calculation, the geologists thought the Earth was millions of years old, so this would have made sense. But by the time Lord Kelvin did this more carefully, geologists thought that the Earth was at least 1 billion years old. And what Kelvin said is, you geologists, we're the physicists, you're geologists. You must have done something wrong. But it turns out the geologists persuaded the physicists that the Earth is billions of years old. And as time progressed, people had more and more accurate ways of measuring the age of the Earth. And in fact, the Earth is about 4.5 billion years old. So much older than 18 million years. So people didn't know, well, what was the power supply of the Earth, of the sun rather, until Einstein came up, and he realized that there was an equivalence between the mass of an object and the energy it contains. So this E equals mc squared. So what is that going to have to do with what's going on in the sun? And maybe I'll make the lights a little brighter, but we can see. So an astronomer named Eddington, what he noticed is, first of all, the most common elements on the sun, or in the sun, are the 2 most simple atoms that we have, hydrogen and helium. Now, if we look up at this table, underneath hydrogen, not everyone will see this, but there's a number, and that's the mass of a certain amount of hydrogen, a certain number of hydrogen atoms. And under helium, there's also a number, right? And what Eddington noticed, and maybe you can notice too, is that if you take 4 hydrogens, right, I'll get, it's 00794, that's almost 008. If I multiply that by 4, I will get 40032. And if you look under helium, it's a smaller number. It's 40026. So if there was some way you could take 1 kilogram of hydrogen and somehow take the nucleons, the neutrons and the protons and the electrons that make up that hydrogen, and rearrange them into helium, you would get slightly less helium in weight. The mass would be 993 grams. So you could rearrange the particles that make up these 2 atoms, that make up hydrogen, and rearrange it and make helium, and the mass goes down a little bit, but what that means is that there's energy released. There's some energy release. So when you turn hydrogen into helium, you lose 7 parts per 1,000 of the mass, which, according to Einstein, comes out as energy. So what happened to the mass, right? So, and how does this process actually work? So let me just... So what's happening now is inside the sun, there's lots of hydrogen. And hydrogen, the electrons have been stripped off the hydrogen. And so what you have is two hydrogen nuclei, which are just protons. And two protons, they repel each other, right? They don't want to come together. They both have positive charge. So what's going to happen in the sun is the two protons will come together, and they don't have enough energy to touch. They'll come together, and they'll just bounce off each other. And they do that for a given proton. It will do that bouncing thing for billions of years, because that's actually how long the sun lasts. But there's a tiny chance, because a proton is a wave, that the two of them, when they come close together, a little bit of this proton will overlap a little bit of that proton, and they can interact with each other. And what actually happens in the sun, if they just interact with each other, that's not enough. Two protons won't stick together. What has to happen is one of the protons will change its identity, and turn into a neutron at that very moment, and then they stick together. So the first thing that happens is the proton sticks with another proton, except at that moment the second one turns into a neutron. Now you have two particles stuck together, a proton and a neutron, and that's something we call that deuterium. It's another type of hydrogen. And then that guy can continue to react and make helium. But the key thing is that releases energy, those steps. And one can worry about exactly what the steps are. So when the neutron is formed, it has to emit, another particle gets emitted, an anti-electron, a positron, and that will annihilate with another electron around there. So we have a few steps that happen where the mass goes away. An electron will vanish. When the different particles stick together, energy gets released, and a proton changes into a neutron. So it's kind of complicated story, but basically all you have to do is think about what was before and what was after, and this missing 7 grams per kilogram tells you how much energy is released. So how much energy is released when a kilogram of hydrogen turns into helium? And how long can this go on? So again, we have this same idea of some energy formula that we want to use. So what's the total energy available to us? And here we're going to use not gravitational energy, but the energy that Einstein identified that's associated just with the amount of matter that's in something. So the amount of, if we take 1 kilogram of hydrogen and turn it into helium, the amount of mass that's missing is 7 grams, which is not very much maybe, but we get to multiply that by the square of the speed of light. So the energy that we get for each kilogram is 6 times 10 to the 14 joules. It's a lot of energy by any standard. It's a lot of energy. And we could think about, and this process of turning hydrogen into helium in different ways is what powers nuclear weapons, right? So we have a tiny amount of mass involved, 1 kilogram, and we get a huge amount of energy out of it. So this is how much we get per kilogram, and we have to go how many kilograms are in the sun to figure out the total energy budget of the sun. Not every atom in the sun is hydrogen. By mass, only 70% is hydrogen, so we multiply the mass of the sun by 70%, and that gives us the mass of hydrogen in the sun. And now we can just multiply those two, and we get the total energy reservoir. It's 10 to the 45 joules. Still a huge number, but you remember the other one was 10 to the 41, right? This is 10,000 times larger energy reservoir than the gravitational energy. So we can figure out how long that would last in the same way, and we get 70 billion years. So much, 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 much longer than the age of the Earth. So this is not how long the sun will last. Don't think that we're going to be sitting here for 70 billion years. Other things will happen before it entirely runs out of fuel. But there's enough fuel in the sun to keep it going for a very, very long time. So how does the sun do it, right? So inside the sun, as you go deeper and deeper in the sun, just like if you go deep in a swimming pool or in the ocean, the pressure increases. The pressure increases just because there's more and more material above you, and the pressure at a given location is how much material there is above you times how strong the gravity is. So the pressure is increasing as you go deeper and deeper, and this equality of the pressure increasing and due to the force of gravity is called hydrostatic equilibrium. So hydro means fluid. Really, it means water, but that's okay. Static means not moving around, and equilibrium means an equality, or also not moving around. So this hydrostatic equilibrium means, although at the surface of the sun, we have an idea of what the density and temperature is, as we go deeper and deeper in the sun, both the density and the temperature get higher and higher, and their product is the pressure. So if we think about what's going on as we get deeper and deeper, we have different things happening as we start at the surface of the sun. The material is rolling. It's going up and down. The material is going up and down like in a boiling pot of water, and we call that convection. So material moves up and falls back down, and that's how the heat gets carried from inside the sun out. So if you remember, the inside of the sun is hotter than the surface, so energy is always flowing out of the sun, and one has to think about how that will work. As you get deeper in the sun, then it becomes more efficient, or for radiation to just be, for energy to be just carried by light bouncing around. And we call that region the radiative zone. And this is important for how long the sun will last. Right in the middle of the sun, we call that the core, and that's where it's so hot that the actual nuclear reactions are going on. And that's a relatively small region in the middle of the sun. And the mass of that region is maybe only 15% of the whole mass of the sun. So now you can see why the sun won't last the full 70 billion years. Because in the sun, the only material that can actually undergo the nuclear reactions and supply energy is right here in the very center of the sun. And once this material is exhausted, the sun will move on its way. It won't have nuclear reactions right in the center, and it will become a different kind of star, and we'll learn about that later. But the time scale for all that to be gone is about 10 billion years. So we've already used up half of it. The sun is now about 5 billion years old. And as the amount of fuel in the middle gets exhausted, the sun changes very gradually. It gets hotter as the fuel gets exhausted in the middle. So the sun today is a bit brighter and a bit hotter than it was a few billion years ago. Now, we can't blame global warming on that. That warming happens on billions of year timescales, not thousands. So basically, the idea of the convection is just that material is actually moving up and down, right? but it's restricted to the outer layers of the sun. Now, we can think of other kinds of stars, and we'll talk about other kinds of stars. If we have a star who's much less massive than the sun, this convection zone gets deeper and deeper and deeper. And now imagine we have a star where the convection zone reaches all the way to the very middle of the star. That's brilliant, because what that means is as the fuel gets burnt in the center, the convection brings new fuel into the center. So those stars who are maybe 50% of the mass of the sun or less, they get to consume the entire star of fuel, right? They live really long time, like 1 trillion years. So 100 times longer than the sun. But our sun has this sort of structure. And if we go to a more massive star, this inner region down here becomes convective, which also means now it gets to exhaust all the fuel right in the middle, which our sun actually doesn't get to do. So let's look at what's going on here. Like, what is the temperature of the sun, the density, as a function of how far out we are in the sun. So on the left-hand side, it shows the temperature. So if you remember, the temperature at the surface was 5,000 degrees. When we go all the way into the center, it's up at 15 million degrees, you can see there. It is 3,000 times hotter in the middle than at the surface. If we look at the density, if you remember, the average density of the sun was about 1 gram per square cubic centimeter. And in the middle of the sun, the density is larger than any material we have on Earth. It's 150 times that of water. So it's much higher density, but it's very hot. So it's still a gas. It still acts like a gas. So that's what's on the left. On the right, it shows where the energy is being made. So you can see we have the fraction of the solar radius, and you can see where is the energy being made is in the top plot. And you can see nearly all of the energy is generated within 1/5 of the radius of the middle of the sun, right? So it's right in the middle. Most of the rest of the sun isn't doing very much, okay? And so, but that region is not convective. So what's happening is, if we look in the bottom, that shows how much fuel is left everywhere. And you can see in the middle of at the outer edge of the sun, it's 70% hydrogen. But when we get to the middle, it's already, like I said, we're halfway done. It's only 30% in the middle. You can see more than half, or about half, of the hydrogen in the middle of the sun has already been turned into helium. Okay? And it just keeps going down. And in a few billion years, that line will reach 0 in the middle. And then the sun will change its structure, which will be bad for us. It'll be a bad thing. The sun will get much brighter, and it'll get bloated. So what the star does is, as it uses more and more hydrogen in the middle, initially it was just a straight line all the way across. It just went like this. And this little deficit here is the amount of fuel that has been used so far, and it will go all the way to this point where it goes like that. And then the sun will change what it's doing. So you can see how much fuel is left, and we have about 5 billion years left of fuel. And as that decreases with time, the star gradually gets a little brighter and a little hotter. So what are the reactions? So Eddington found the fuel. How exactly does it do it? I described it in a little bit earlier to motivate it. But if we think about it at the temperatures of the sun, 2 protons, they're coming close to each other, but they both have positive charge, so they want to be repelled, but they have energy, so they can come pretty close, and it seems really close. 10 to the minus 12 meters, that seems awfully close. Seems like it's going to be good, except protons are much smaller than that. They are about 1,000 times smaller than 10 to the 12 meters. So what's going to happen is they get close, but they're still 1,000 proton sizes away. They're not close enough to stick. They don't have enough energy to get close enough. So how do they stick together? So basically, the protons run into this wall of repulsion, and according to classical mechanics, it's literally like a wall, and me running into the wall. And the proton will keep bouncing off the wall, just like I'm bouncing off the wall now. However, like I said, the proton is a wave, right? It has a little bit of, it's not exactly in one place, it's spread out. And sometimes the proton breaks through the wall. And it's literally like me, if I ran into this wall many, many times, eventually I would go through it, believe it or not, but it would take longer than the age of the universe, because I'm big. But protons have very low mass, so the chance of them penetrating through the wall is a lot higher than me going through. And like I said, even if they break through, almost always they kind of go, hey, we've been bouncing back and forth for thousands of years, and finally we meet up. And the proton goes, hey, you're another proton. I don't want to stick with you. And they fly apart again. But sometimes something else happens. And the two protons come together, and at that very moment, a proton can choose to change into a neutron. And so the two protons come together, and they're saying, hey, you're a proton. And the other one says, actually, I'm now a neutron. And they can stick together. The proton and neutron can stick together, and this is the reaction that you get. So the protons come together, and coming out the other side is a deuterium nucleus, which is a proton plus a neutron, and you get two other things coming out. One thing called a neutrino, which I talked a little bit about, but we can talk more about a little later. Neutrinos don't interact with matter very much, and it can just fly and leave the sun. And the second thing that comes out has to carry the positive charge of the proton, and what it is an anti-electron, or what we call a positron. So if we look at the whole process going on, we have two protons coming together. They make a deuterium. The deuterium picks up another proton, makes a type of helium now. We know it's helium because it has two protons in it. But this helium only has 3 particles in it, so we call it helium-3. And we'll get 2 of those helium-3s sticking together, and at the end, the net result is we have a helium-4 coming out, and 1, 2, 3, 4 helium. You can see there's 6 hydrogens involved here, but 2 come out the other end. So we have 4 hydrogens make 1 helium, which is just what Eddington ordered. And there's a few other particles that were thrown out. There's some gamma rays, which are just carry energy, and it heats up the gas. There's this guy, which is a positron. It's an anti-electron. So it travels for a little while, and guess what it does? It bumps into an electron. It makes more energy. And finally, you have the neutrino. So people went, okay, this is how it works. How can we be sure? We can make a model of the sun, and it seems to check out. But ultimately, these neutrinos leave the center of the sun and come to us on Earth. And if we can detect those, we can see that these reactions are indeed going on. Now, there's other reactions that happen, which is this is kind of a more complicated one, which goes in a circle. In the sun, it has other atoms in it, like carbon, and this a small fraction of the energy of the sun is produced in this way, where carbon it just goes in a circle, so you can start wherever you want. Let's start here. So carbon can get a proton and make nitrogen, and then the nitrogen decays and it emits a neutrino. and it goes around and around like that. And then the new type of carbon picks up another proton. You just go around in the loop, and you end up right where you started, except you have a helium popped out, and the same number of hydrogens were absorbed. 1, 2, 3, 4, right? And this one also makes neutrinos. And these neutrinos have very specific energies. So we can look for those neutrinos as well to take the temperature of the sun. And as we go to hotter stars, this becomes more important. This process becomes more important than what goes on in the sun. So everything, we can't see into the middle of the sun. Yes?
How did the sun get carbon and nitrogen?
Oh, it turns out there were stars around before the sun, right? So there's also carbon and nitrogen, oxygen on our planet, which came from when the sun was born too. So all of those elements got produced in other stars. And then you could ask the question, are there any stars so far that we've discovered with no carbon in them? And the answer is no, right? Every single star, some of them have 1/10,000th the amount of carbon of our sun, but they still have a little bit of carbon. So we still have to discover the stars that made the first elements, right? And that's why we build these bigger telescopes, to see them. So how do we know? And we'll learn where all the carbon comes from. Don't worry about it. It'll happen. So it's a good question. So how do we know what's going on? Everything is sort of hidden except for the neutrinos. And there's another way we can measure what's going on in the middle of the sun that I'll talk about too. So these neutrinos from the sun are coming through us all the time. And in fact, every square centimeter of our body is being crossed by a lot of neutrinos, almost a trillion neutrinos every second. And these neutrinos, they don't do us any harm. They don't do anything. They very rarely interact with matter. So if we think of the photons that are produced by these reactions, they kind of just take a very wiggly path coming out of the sun. It'll take about 1 million years for the photon to finally get out of the sun. The neutrino just zips out of the sun in about a second or two. It just goes in a straight line at the speed of light, and a large number of them are hitting the Earth all the time. So what people did is they tried to make detectors to measure how many neutrinos were coming through the Earth. And the first detector, it consisted of a big tank of carbon tetrachloride. So a carbon atom bound to 4 chlorine atoms. And occasionally what can happen is one of those chlorine atoms can absorb a neutrino and become an argon atom. So you can see where chlorine is on the table. It can just move one to the right. Now chlorine is very, very reactive. Argon is not. So when the chlorine becomes argon, the argon just will float away from its atom, from its molecule. Right? It'll be carbon bound to 3 chlorines, and then this argon atom just floats to the top of the tank. So what Ray Davis did is he was able to count these argon atoms one by one by one, amazingly enough, right? They're radioactive, so you just had to look for the decay. And, oh, I saw a decay. That must have been an argon atom. And he could put in one atom in, like he would have his buddy put in, I'm going to put in 4 radioactive argon atoms. And then Ray Davis would empty the tank and count the argon atoms and said, did you put in 4 atoms? And the guy would say, yes. It was that level of precision. He could count the atoms. And what he found was they knew how hot the sun was, they knew what was going on, but they only got 1/3 of the neutrinos that they expected. And later on, there was another experiment called Kamiokande, which measured neutrinos entering a big tank of water, and occasionally the neutrino would interact with the oxygen or the hydrogen in the water and make a little flash of light. And they counted the neutrinos. And They, I think, got half the number expected. Weird. They both won Nobel Prizes, right? That's what the little Nobel Prize symbol was. So what was going on? So did we not understand what was going on with the sun? There was also another Nobel Prize for this recently to a Canadian called, why am I forgetting his name? Art MacDonald, who is at Queen's University. So the solution to this problem was like our Superman. And what do I mean? Like when you're looking around for Superman, you often don't find him because he's in that very sophisticated disguise there, right? But he's still around. So it turned out that the experiment of Ray Davis could only find neutrinos of a particular type, neutrinos who are called electron neutrinos. Let's imagine that's Superman. And the sun only makes electron neutrinos. So that made sense. Except what they realized between these two experiments was not that the sun was making too few neutrinos, but the neutrinos were changing their identity on their way from the sun to Earth. So they would get dressed up as Clark Kent, 2/3 of them. And 1/3 would still be an electron neutrino. So it turns out, once again, the astronomers were right and the physicists were wrong, that the sun was working just fine. It was just the neutrinos had different properties than we thought they did, that they could change their identity as they travel along. So another way that we can look inside the sun is that the sun oscillates like a bell, if you want. And by measuring the frequencies of a bell, for example, if you listen to a bell and you know how big it is, you can figure out what the bell is made of, if you really think about it. So the sun, we know how big it is, we can measure the frequencies, and in that process we can figure out what the structure is inside of the sun. It's very similar, we call this helioseismology. On Earth we call it seismology. When there's an earthquake, we can use how the waves propagate around the Earth to figure out the internal structure of the Earth. We can do the same for the sun, and that checks out, right? So we can use this to measure what is the temperature going into the sun, and that agrees with what we expect.